Welcome to the fourth lecture of the Digital Image Processing course. In today's lecture, I want to continue the talk on spatial filtering, and then at the end, I will give a brief introduction to uh, Fourier transform that will be covered in much more detail in the following lectures. So, in today's lecture, I will talk about the smoothing or low-pass spatial filters. I will talk about sharpening or high-pass spatial filters. I will talk about high-pass, bandreject, and bandpass filters and how we can make them by only using low-pass filters. And then how we can combine a spatial enhancement method that we discussed so far. So basically intensity transformation and spatial filters all combined to give us the needed result for one example. If you remember from the previous lecture, I mentioned that there are two main components in any spatial filter definition. We have a neighborhood, and then we have an operation that is defined in that specific neighborhood. So let's just assume we have this image that is placed in this coordinate system. Along X we have the rows and along Y we have the columns. So let's just say we want to define a spatial filter in this neighborhood defined by 9 blue squares. So for this neighborhood we have a kernel in which its center is basically the middle pixel of the uh, kernel, and this kernel has a bunch of weight associated with each one of the elements of uh, the kernel. So not only it defines the size of the neighborhood, but also it defines the weight that will be used to perform the needed operation. So this kernel is moved pixel by pixel across the image, and at each pixel location, these weights are multiplied by the corresponding image pixel intensities, and then they are going to sum up to produce the final result. So one thing that you should notice is that that is only one way that we can have spatial filtering. In fact, there are two ways we can have spatial filtering. We can have linear spatial filters in which uh, the procedure, as I described, is basically producing some element-wise multiplications and then summing all the results to get the final value for the uh, response of the image to the filter. But we can have nonlinear spatial filters in which the procedure is a bit different than linear ones. So here we talk about median filtering, which is a nonlinear spatial filters in the uh, next uh, in the following slide. So let's just for now focus on linear spatial filters. As I said, linear spatial filters produce a sum of product operation between an image and a filter kernel. Here we call the kernel W. So the kernel by itself is an array which not only defines the neighborhood of the operation, but also it has some coefficients or weights that determine the nature of the filter. So depending on the values of these weights, we can have different types of linear kernels. A kernel is also called a mask or template or a window. So here you see an example of a 3 by 3 kernel. So at any point X and Y in the image, we can calculate the response of the image for that pixel. We denote it by g of xy, and g of xy is the sum of product of the kernel coefficients and the image pixel that are contained in the area specified by the kernel. So as you can see, each one of these weight is multiplied by one pixel, and then they all are summed together to create the final result for the image. As we change the coordinate of x and y, we basically move the center of the kernel, so it goes over all the pixels inside the image. It is very common in image processing applications that we use kernels of odd size dimensions in both x and y directions. So if we have a generalized kernel of odd size dimensions, we can basically say the size is lowercase m by lowercase n, and then we can represent m and n by two values, two integers a and b, and then based on those, the range of the values of m is mentioned to be from negative a to a, and the range of the values for n is going to be from negative b to b. So that way we can simplify the previously mentioned equation in this very nice and compact form. The mathematical equation that we saw in the previous slide is what is usually called a correlation operation, which is usually either showed using a hollow star or a circled plus sign. So here you can see the same equation but only for a one-dimensional function. So let's just see how this can be done uh, for a one-dimensional image with a one-dimensional kernel. So as you can see, we have an image that has 8 values, but it's only one-dimensional, and we have a kernel that has 5 values. So the center pixel for this kernel is going to be bit value 4. So since we want to find the response of this image to this kernel, we have to basically align the center with the first pixel and then calculate the response and then move this one place to the right until we get to the end of the image. But the first thing that we notice here is that when we align the center of the kernel with the first pixel of the image, there are two values that fall outside the boundary of the image that we have. So in effect, the calculation is undefined for these two values. To avoid that, one of the common ways is to zero pad the image so we don't have any undefined operation. So since two elements of the kernel fall outside, when we align the center with the first pixel, we add two zeros and then we calculate these element-wise multiplication. So we have 1 multiplied by 0 plus 2 multiplied by 0 plus 4 multiplied by 0 all the way to 8 multiplied by 0. So the result for this is going to be 0. So we put 0 here. Then we move the kernel one step to the right and then do the same. The result will be 8. Then the next one result will be 2, then 4, then 2, and then finally 1. And then when we move completely to the right, we have two additional zeros at the end too. So this is what is called the result of correlation of this image with this kernel that we have. One thing that you notice is that our image has only one value that is non-zero, and this is generally considered as to be a discrete unit impulse. So the general definition for such function is mentioned here. So delta of x minus x0 is 1 if x is equal to x0, but it's 0 otherwise. So for example here, if we assume this as the first, basically the 1 and 1 location, the origin of the image, so this function f is going to be delta of x minus 4 because it is 1 when x is equal to 4, otherwise it is 0. Another thing that you notice is that when you find the correlation between this discrete unit impulse and the weight, what we get is basically a reverse version of the kernel at the location of the discrete unit impulse. But again, the whole point is that this result is a rotated version of the kernel. So now let's say, what if we want to have the exact same copy of the kernel? So what should we do? The way to do it is basically to rotate the kernel 180 degrees before the correlation and then do exactly the same. So we have this image, we rotate the one-dimensional kernel 180 degrees, basically rotate it around its center, and then we get this rotated kernel, and then we basically follow the same procedure as the correlation. So we place the center at the first pixel. We realize that there are two values of the kernel that fall outside the boundary. We add zeros, and then we calculate the element-wise product, and then sum the result to get the final response of the image to this pre-rotated kernel. So when we do that, now we see that the convolution result is basically the exact copy of the original kernel at the location of the discrete unit impulse. So pre-rotating the kernel results in an exact copy of the kernel. So now let's just see what happens if we have a 2D image. For 2D images and 2D kernels, the first thing that you notice is that we have extended these two equations for correlation and convolution to include two variables that are changing. So the image that we have here is again a discrete unit impulse, but it is in two dimensions. So the definition that we have is delta of x minus x0 and y minus y0. It is 1 if x is equal x0 and y equal y0, otherwise it is going to be 0. So if we assume the origin to be here, so 1, 1 location here, this is going to be a delta of x minus 3 and y minus 3, because at location 3 and 3, the value of the function is 1, otherwise it is 0. And the kernel that we have is a 3 by 3 kernel. So the first thing that we need to do is that we have to align the origin of the kernel, which is its center pixel, with the first element of the image that we have. So if we do that, we realize that there are some values of the kernel that fall outside the boundary. So to avoid undefined operations, we zero extend the image. So there are no values of the kernel that fall outside the boundary. And then we basically repeat the procedure. So we find the element-wise multiplication between each kernel element and each image pixel, and then we find the summation. We move to the next pixel, we repeat the same, we move to the next pixel, we repeat the same until we get to the end of the original image. So if we do that for the correlation result, as you can see, we get a replica of the kernel, but the difference is that the kernel is now flipped in both horizontal and vertical direction. So now let's do a similar thing as we did before. So we pre-rotate the kernel along both of its directions. So we basically flip it around the horizontal direction and then flip it along the vertical direction to see what we get. So this is the rotated two-dimensional kernel. And if we find the correlation between this kernel and this image, now we have the result of the convolution, which is the exact copy of the original kernel. So by itself, correlation and convolution, they may look almost identical, and the whole point of rotating the kernel may not be obvious. But if we look at the different properties of correlation and convolution, we realize that convolution is much more superior uh, than correlation, and that's why for linear spatial filtering we generally use convolution instead of correlation. So let's go and check out the properties of correlation and convolution. So the first property uh, that we want to discuss here is the commutative property. So this is a property that is satisfied with the definition of convolution, but it's not satisfied with the definition of correlation. So if we find the convolution of f and g, it is the same as finding the convolution of g and f. So that means that the order of the functions that are going to be convolved is not going to be important. In another word, it doesn't matter if you rotate the kernel or the image, you still get exactly the same result. But you cannot say the same thing about the image. So about the correlation. So that is one good property of the convolution that is not present in correlation. The other good property is the associative property, which basically says if you convolve f with the result of convolution of g and h, it is the same as convolving h with the result of convolution of f and g. And that is a property that is not satisfied in the correlation. And finally, we have the distributive property, which says that you can distribute both convolution and correlation over summation. So this is something that is common between both convolution and correlation. So because of the commutative property of the convolution, as I said, it's not important whether the kernel or the image is pre-rotated. Also, because of both the commutative and associative property of the convolution, you can perform multi-stage filtering by just simply convolving all the kernels first and then uh, filter the image using the result of the convolution of all the kernels. Also, what we saw last time was that if we have separable kernels, we can use this associative and commutative property to basically reduce the computational time for the convolution significantly. So this is something that will be discussed a little bit later on as well. So now that we had a quick overview of what we discussed last time, let's just start talking about the spatial filters. So the first spatial filter that I want to introduce is the smoothing or averaging spatial filter, which is used for reducing sharp transitions in intensity of the images. So random noise also introduces sharp transitions in the images as well. So smoothing or averaging can help us reduce noise too. Another application for a smoothing spatial filter is to reduce aliasing in the result of resampling of images, but this is something that will be discussed in much more detail in chapter 4. We can use the smoothing to reduce false contouring. If you remember, false contouring was the result of using not enough number of bits or intensity level to show an image. So if you have an image, let's say that is coded using 3 bits and you want to convert it to an image that is coded using 8 bits, you will see a lot of false contouring, but by applying a smoothing a spatial filter, you can reduce the effect of false contouring. So there are two types of smoothing filters. In fact, there are more than two types of smoothing filters, but in general, we have again linear filters or non-linear filters. So in the class of linear filters, We can have box filter kernels and low-pass Gaussian filter kernels as examples. And for the nonlinear filters, we can have order statistic filter. For example, a median filter is one of the order statistic filters. So box filters are simple separable low-pass filter kernels in which all the coefficients of the kernel are exactly identical throughout the whole neighborhood. So if we have an m by n box filter, uh, the box filter is basically a matrix of size m by n with all the values being 1, but to reduce, basically to not introduce any bias into the image, we apply a normalization constant uh, before the kernel. So basically we scale down all these ones to not introduce any bias into the final result. So for example here, since we have a 3 by 3 kernel, we want these values to add up to 1, and that's why we multiply the whole thing by 1 over 9. So if we had a kernel that was of size 5 by 5, the normalization constant would be 1 over 25. So why normalize the kernel? Because we don't want to introduce bias into the image. So an area of constant intensity in the image should remain the same after filtering. And preventing bias during filtering means that some of the pixels in the original and filtered images are, are staying the same. So let's just see how this filter can help us in smoothing an image. So on the top left corner we have the original image, which is of size 1024 by 1024 pixels, and the rest of these images that we have are smoothed using kernels of size 3 by 3, 11 by 11, and then 21 by 21. One thing that you can see is that when we are working with kernels of a smaller size, the effect is minimal, so there is not that much distinguishable differences in terms of smoothing from the first image to the second image. But as soon as we increase the size of the kernel of the box filter, we see that we have more and more smoothing, to the point that there are some fine details that are hardly visible in the image. So for example, the pattern inside this square, when we use a kernel size of 21 by 21, it's not visible. Or for example, this lowercase letter A is hardly visible. One other thing that you might notice is that when we apply the box filter, there is this faint gray border that appear at the end after you finalize the result, and this is as a result of zero padding the image to avoid the undefined operations when part of the kernel is outside the image's boundary. Box filters are very simple and suitable for quick implementations, and they are very useful when we want to reduce the effect of smoothing on edges. But box filters by no means are the only possible smoothing kernel that you can have. In fact, you can have infinitely many different um, smoothing kernels, all with random weights, and each one can have a different effect. So that's why we introduce here the Gaussian filter kernels. So box filters are generally poor approximations of blurring characteristics of lenses, and box filters also favor blurring along the perpendicular lines because there is a dimensionality associated with box filters. Uh, if you, for example, rotate the box filter 45 degrees, you don't get exactly the same filter as before. So that means that they have preferences in terms of the directions of uh, the edges or the features that they smooth. To avoid these shortcomings, it's better to use circularly symmetric or isotropic kernels, which means that no matter how much you rotate the kernel, you still get exactly the same result. So one of these types of kernels is the Gaussian kernels, which is not only circularly symmetric, but also it is separable. So the general definition for a Gaussian kernel is something like this. We have the kernel with continuous variables s and t, and the equation is defined as this. We have k, which is a constant showing the strength of the kernel, and we have e to the power negative s squared plus t squared over 2 sigma squared. So to signify the circularly symmetric form of the kernel, it is very common to replace s squared plus t squared with r squared. Basically, when we consider the center of the kernel at 0, then we define a circular neighborhood around the kernel or around the center, and based on the radius of that circle, we define the distances, and therefore we define the coefficients for the kernel. So this simple figure shows values of the radius from the center that we can use for defining different uh, Gaussian kernels. So for example, if we want to define a Gaussian kernel of size 3 by 3 for the pixel at the center, the value for r will be 0. For all the immediate neighbors, the value for r will be 1, and for the diagonal pixels or the diagonal element of the kernel, the value for r will be the square root of 2. So if you replace r for each one of these and you predefine the value for k and the sigma, you can basically come up with the weight for your kernel. So this is what is called sampling, because the Gaussian function is a continuous function and cannot be applied directly to the image. So because of that, we need to sample it at integer spatial location and make a discrete kernel. And as before, since we don't want to introduce any bias to the final result, we normalize the kernel by dividing all the coefficients by the sum of the coefficients that are contained inside the kernel. So for example, here is an example of a Gaussian kernel of size 3 by 3, in which k is chosen to be 1 and sigma is also chosen to be 1. So as you can see, we have this normalizing constant right before the kernel, which is 1 over the sum of all the values of weight inside the kernel. Since Gaussian kernels are circularly symmetric and separable, you don't have to sample in 2 dimensions. You can just simply sample along a cross section that goes through the center of the kernel and then convert it to a 2D kernel by the procedure that I explained in the previous lecture. So values of a Gaussian function at distances that are larger than 3 sigma from the mean are very, very small. So we can select the size of the Gaussian kernel to be at max 6 sigma by 6 sigma. So this symbol basically shows the ceiling of the value inside of it. So if we have, let's say, if you want to define a kernel with sigma of 3.5, the maximum size that we can have for the sigma without having any significant effect, uh, since we eliminate some of the Gaussian values, is 6 multiplied by 3.5 or 21 by 21 pixels. One other nice property of the Gaussian kernels is that the product and convolution of two Gaussian kernels is going to be also Gaussian. So if we have f and g as two Gaussian uh, functions with their own mean and standard deviation, the result of multiplication gives also a Gaussian kernel which has this mean and this standard deviation. If we do convolution of the two functions, again we get a Gaussian function that has this mean and this standard deviation. Of course, I'm not going to go into detail of how these values are derived, but you can easily do it yourself. So now that we saw how Gaussian kernels are defined, let's just look at one example. So here we again have the test pattern that we use for the box filters too. So this is the result of low-pass filtering using a Gaussian kernel of size 21 by 21 with a standard deviation of 3.5. This one is the result of Gaussian filtering using a kernel size of 43 by 43 with a sigma value of 7. As you can see, as we increase the value of sigma and consequently we increase the value of basically the size of the kernel, we have much more blurring. And one other thing to notice is that this blurring is much more uniform in all directions, unlike the box filter, which was giving preference to edges or features that are in perpendicular direction. As for the size of the kernel, we have these two results here. One is acquired using a Gaussian kernel of size 43 by 43 with sigma equals 7. And this one is the result of using a kernel size of 85 by 85 with exactly the same value for sigma. So here the sigma is 7 too. And this is the difference image between these two filtered results. So what you can see is that the difference image is all black, which means that there is no significant difference between these two images. So by considering sigma, we can have a good limit on the size of the kernel that we are going to use as well. So there is no point of going any larger than 6 sigma in the image. Of course, it is not necessary to stay at 6 sigma. Going beyond that, going over 6 sigma is not beneficial, but going below 6 sigma in some applications it is used. So now that we saw both box filters and Gaussian filters being applied, let's just talk a little bit about different types of padding that we can have. So far what we used was that we used zero padding to avoid the undefined operation. But zero padding is not the only way possible for padding an image. So in addition to zero padding, we can have mirror or symmetric padding, in which values outside the boundary are obtained by mirror reflecting the image across the border. And we can have replicate padding, in which we replicate the values for outside the boundary equal to the nearest image border value. So you see the effects of different types of padding here too. So here we have the result of filtering the test pattern using a Gaussian kernel of size 187 by 187 with k being 1 and sigma being 31. This one we use zero padding to avoid the undefined operation. For the next one we use mirror padding, and for the third one we use replicate padding. As you can see in the zero padding result, we have this gray border across the final result, but this is not something that can be seen uh, for the mirror padding and replicate padding. So usually in practice, mirror padding and replicate padding are more common. So as you saw, we can use a smoothing to basically eliminate or smooth out the fine details of the image. So the level of this elimination can be specified by the size of the kernel that we are using. So if we are using a box filter, the size of the kernel is directly related to the amount of smoothing that we get. For the Gaussian kernel, the size of the kernel is one factor, and the other factor is basically the sigma of the Gaussian function. So let's just see one example of how smoothing can be used for shading correction. So this is uh, an image that we already saw before of this checkerboard pattern that is non-uniformly illuminated. So one thing that we said before was that to get this image corrected, if we have a good estimate of the shading of the image, we can use arithmetic operations to basically get rid of that. So one way that we discussed last time was that if we have access to the device that is used for scanning this image, and then we scan a blank sheet of paper, we can get a good estimate of the the shading. But what if we don't have access to the scanning device? So can we use the original image to get a good estimate of the shading? That is exactly what we did here. So the original image is of size 2048 by 2048, and each square is of the size 128 by 128. So the middle image is the result of applying a Gaussian kernel of size 512 by 512. And as you can see, since the size of this kernel is very large and also the sigma is very large, we are basically eliminating the very fine details in the image. Here will be the grid, basically the black and white circles, sorry, squares that we have in the image. So at the end, what we get is basically a highly smoothed version of the original image, to the point that the squares are not visible anymore. But what is visible is the general shading of the image. So if we use arithmetic operation as we discussed before, we can get an image that its shading is corrected. So that is one application of low pass filtering. So now that we saw two examples of linear spatial filtering, let us look at one example of a nonlinear filter. So order statistic filters are nonlinear filters that work based on ordering or ranking of the pixels in the region that is encompassed by the neighborhood. So unlike the linear filtering in which we produce a sum of product form, here the kernel only specifies the neighborhood, but we don't have any weight. So what we do is that we basically order all the pixels that uh, are within the area of the neighborhood, and then we replace the value for the center pixel by some ordering operation. So one example is the median filter, in which it replaces the value of the center pixel by the median of the intensity values that are present in that neighborhood. Median filter, is very useful for reducing salt and pepper noise. Uh, so the way that median is found is first we order all the values of intensities in the neighborhood. If we have several values that are the same, they will be grouped together, and then we find the value for which half of the intensity values are less than the median and half of the intensity values are greater than the median, and that value is basically the value that will be placed or the center pixel. So you see one example here. Here we have an X-ray image of a circuit board that is highly cropped by salt and pepper noise. And salt and pepper noise uh, is generally different than the Gaussian noise. So Gaussian noise is basically you can think of as additive noise, but salt and pepper noise it is a form of like multiplicative noise to some extent, or replacement noise, because some of the pixel values are going to be replaced with very bright values and some of them will be replaced by very dark values. So in the middle you can see the result of noise reduction using a 19 by 19 Gaussian low-pass filter with a sigma of 3. As you can see, the amount of noise is reduced, but at the same time we still have noise and there are much blurring in the areas of sharp features or edges in the image, and that is something that is usually not uh, desired. Instead of median Gaussian filtering, if we use a 7 by 7 median filter, this is the result that we get. And as you can see, the image is almost completely noise free and a lot of the sharp features are still preserved. But you should keep in mind that median filtering, even though it is very good for salt and pepper noise, it's not necessarily the best solution for all types of noise filtering. On the other hand, you have to consider that Gaussian filtering is one example of a smoothing filtering, not the only possible way. So there are much more advanced filtering techniques that not only can get rid of the noise but also preserve the details and the sharp transitions in the images. So uh, only consider the Gaussian filter and the medial filter as two basic filters with nice properties, but they are not definitely the only type of filters that we can have in image processing. So now that we saw how smoothing or averaging spatial filters work, let's just talk about sharpening or high-pass spatial filters. So in sharpening filters, we want to highlight or boost the intensity transitions within the image. So if we associate averaging or smoothing with the integration of the image, then sharpening is associated with the spatial differentiation. So image differentiation helps us to enhance the edges and other discontinuities in the image like noise, but at the same time de-emphasizes the areas of slowly varying intensity. So before we go um, into much more detail, let's just quickly go over some of the properties of the first derivative and the second derivative of a function. So for the first derivative of a function, the first derivative is 0 in areas of constant intensity. It is non-zero at the onset of an intensity step or ramp, and it must be non-zero along intensity ramps. As for the second order derivative, it must be 0 in areas of constant intensity. It also must be 0 along intensity ramps, but it must be non-zero at the onset and end of an intensity step or ramp. So now since we saw the properties, let's just see how it works in images. So for digital functions, the derivatives are usually defined in terms of differences. So the first order derivative of a 1D function in a difference form is defined like this. So derivative of f with respect to x equals f of x plus 1 minus f of x. So in essence, for location x, what we do is that we subtract the intensity value of its next pixel and the intensity value of that pixel, and based on that we get the first order derivative. As for the second order derivative, it is similar to applying the same equation twice. So the second order derivative of f with respect to x is going to be f of x plus 1 plus f of x minus 1 minus 2f of x. And here we use partial derivative because we want to have consistent notation when we go from a one-dimensional to two-dimensional function. So these two are defined here only for one-dimensional function. So let's just see how they perform when we apply them to this one-dimensional curve here. So you can consider this one-dimensional curve as a one-dimensional image that has three areas of constant intensity. We have an intensity ramp, and we have this intensity step that is basically a sudden change from a lower intensity to a higher intensity or vice versa. But the important thing is that this step happens only within the uh, length of moving one pixel. So let's just see how these two first and second derivative can be applied. So the values of this one-dimensional image are mentioned here. So for the first derivative, as said, for any pixel, we get the value for the pixel in it to its right, and then we subtract the value with the value at that exact pixel. So for example, for this pixel, for the first derivative, we have 4 minus 5, which is -1. As for its second derivative, what we have is f of x plus 1, which is here 4, minus f plus f of x minus 1, which is here 6, minus 2f of x. So for this pixel, it's going to be 4 plus 6 minus 10, which is equal to 0. And we do the same for all the pixels of the original image. So when we do this, this is the curve that we get for the first derivative and the second derivative. So the first derivative is shown with this filled circles, and the second derivative is shown with this hollow squares. So now let's see what happens first for the areas of constant intensity. So for areas of constant intensity, as we saw before, the first derivative is 0, the second derivative is also 0. So let's just see if this is satisfied. So here's an area of constant intensity, and as you can see, both first derivative and second derivative are 0. Here's another area of constant intensity, and both first derivative and second derivative are 0, and here is another area of constant intensity, and both first and second order derivative are 0. We said that for first order derivative, it must be non-zero at the onset of an intensity step or ramp. So let's just see if this is true. So this is the onset of the intensity ramp, and as you can see, the first derivative is non-zero. Here again, we have this pixel for which basically we have a change in the value of the first derivative. So it goes from a non-zero value to a 0 value. The same is true for this step as well. So at this point, right, we have a sudden change in the value of the first derivative here. So as you can see here, the value for the first derivative and also the second derivative is non-zero. And finally, we said that the first derivative is non-zero in the area of an intensity ramp, but the second derivative is 0 in the area of an intensity ramp. So let's just see how it works. So here we have this intensity ramp. As you can see, the first derivative is non-zero. In fact, it's -1 because the slope of this line is -1, but the second derivative is 0. One interesting thing that you might notice is that for the second derivative, when we go from a higher intensity value to a lower intensity value, we have a second derivative of a negative value. But when we go basically depending on the direction, now here we have a positive second derivative. it is more interesting when we are going through a step. So going through this step, right before the step, we have a value of positive second derivative, and right after this step we have a value of negative second derivative. So because of this we have this zero crossing that can help us to locate the location of the steps, or more generally image edges. You will see examples of how these are useful later on in the course. So now that we saw how we can define the first and second order derivative, let us see if we can come up with ways to use them for image sharpening. So for image sharpening using Laplacian, we are interested in creating an isotropic kernel or a bunch of isotropic kernels with response independent of the direction of intensity discontinuity. So one example is the Laplacian operator, which for two variables is defined in this form. So delta squared of f equals the second derivative of f with respect to x plus the second derivative of f with respect to y. So if we replace these two terms by the definition that we had for the second derivative using two variables x and y, this is the equation that we get for the Laplacian. So uh, delta squared of f equals f of x plus 1 and y plus f of x minus 1 and y plus f of x and y plus 1 plus f of x and y minus 1 minus 4 f of x and y. So we can convert this equation into a kernel like this, in which the value for the center or the origin of the kernel is -4, and all these immediate neighbors have a value of 1. The values for the corner will be 0, so that is what is called a Laplacian kernel. So as you can see, the kernel is isotropic for rotations of increments of 90 degrees. So if you rotate this kernel 90 degrees either clockwise or counterclockwise, you can get exactly the same kernel, and that's why it's called isotropic, but only for rotations of increments of 90 degrees. But what if we want to incorporate the diagonal directions too? So simply what we do is that we apply the same equation for the diagonal direction as well, and then we incorporate those weights into the kernel. So if we do this, the kernel that we end up with has a -8 at the center and all ones around the center. What if the negative sign is used for second derivative? And that is something that sometimes is common too. So basically it looks as if we multiply these two kernels with a negative sign. So by themselves they are not going to be important, but they become important when we want to combine a Laplacian filtered image with another image. So this is something that we need to consider when we want to combine several images. So by themselves, having these as like either positive or negative does not matter that much. But one thing that you should notice is that the coefficients of each one of these kernels sum to 0. So the reason for that, we don't want to introduce any bias in the areas of constant uh, intensity. Because if we introduce bias, that means that the Laplacian operator for the area of constant intensity is non-zero, which is not what we intend to have. So now that we saw how Laplacian can be defined, let's just look at a quick example. So as I mentioned, using Laplacian we can get the fine details of the image. So what we can do is that we can combine the Laplacian of an image with the image itself to basically enhance its fine details. So the equation that we commonly use for the final sharpened image is g of xy equals f of xy, basically the original image, plus c multiplied the Laplacian of the image. So c is a constant that controls the amount of additional detail that we add to the original image. So let's just look at an example. This is a blurred image of the north pole of the moon. Since we want to sharpen it, first we calculate the Laplacian uh, using this kernel here. Then what we do is that we add this image using a value of c equals -1, because if you remember, the value at the center here is -4. So since we want to add these additional details, the value for c needs to be -1. So after adding these two images together, this is the sharpened image that we get. If we use the other kernel, this kernel, with the exact same coefficients of negative, with the exact same value for c at -1, what we have is this image, which is a bit more sharpened, because as you can see from the previous slide, the second kernel is isotropic to kernels to rotations of increments of 45 degrees. So it can preserve much more details in other directions as well. So in general, if we are using these two kernels for sharpening the image, we use C values that are negative, and if we use these two kernels, we use C values that are positive. So we saw how we can use the second derivatives in the form of Laplacian to sharpen the image. What about the first derivative? So the first derivative are implemented using the magnitude of the gradient. So the gradient of a 2D image at coordinate x and y is defined as a two-dimensional column vector. We have the gradient of f, or delta f, equals g of x and g of y. G of x, or gradient in the x direction, is defined as the derivative of f with respect to x, and g of y, or the gradient in the y direction, is defined as the derivative of f with respect to y. So this vector points at the direction of the greatest rate of change of function f at location xy. In another word, this vector is perpendicular to the edge at that location. So since it's a vector, we can have a magnitude and also an angle. So here we work based mainly on the magnitude part. So the magnitude of this vector can be calculated by squaring the individual components of the gradient and finding the square root of that value. So this is going to be called the magnitude image. We show it here by m of x and y, and at each location it is basically the length of the gradient vector at that place. And m basically shows the rate of change in the direction of the gradient. So there is a more computationally suitable approximation that is usually used, in which m of x and y is approximated by the sum of absolute values of g of x and g of y. So similar to Laplacian, we can use derivatives in their difference form, and we can create appropriate kernels for computing the gradients. So here you can see two different kernels. We can have Roberts kernel and we can have Sobel kernel. So this is a generic 3x3 region of the image, in which z values are the intensity values. So these two figures are the Roberts cross gradient operators. As you can see, they calculate the gradient along the diagonal directions. And then we can have the Sobel operators that calculate the gradient along the horizontal and vertical direction. So use of any of these is very common in image processing applications. The way that we do is that we usually calculate the gradient using any of these, and then if you want to create the magnitude, we basically combine the two gradients into a magnitude image. So one example of using first order derivatives is for detecting defects in uh, automatic digital image processing systems. So let's just assume a system that is used to detect defects in contact lenses. So this is an image of the contact lens. So that a specific system is able to detect defects much more easier if we provide the magnitude image. So we have two defects here which probably are not visible that much. So for that specific system, if it's more comfortable using the magnitude image, we can calculate the magnitude image by uh, applying the Sobel operator or Sobel kernels in both horizontal and vertical direction, combine them to create a magnitude of the gradient, and this is the result that we get. And as you can see, the defects that we have in the lens are much more visible in this figure. Another technique that is commonly used for sharpening an image is called unsharp masking. So in this technique, we can subtract an unsharp or a smooth version of the image from the original image to create a mask to sharpen the image with. So let's just look at this one-dimensional example. Here we have this original signal that is basically constant values in two regions and an intensity ramp in the middle. So if we blur the signal, we get a function of this form. Then if we subtract the original signals and the blurred signal, what we get is what is called an unsharp mask. As you can see, in the areas that the intensity or the derivative changes, we have undershoot and overshoot. So now if we sum this unsharp mask with the original image, we get a sharpened image. So in mathematical form, we have to first blur the original image. So we go from f of x and y to f bar of x and y. So we can use any of the smoothing kernels that we saw so far. Then to create the unsharp mask, we subtract this blurred version from the original image, and then we add this unsharp mask with a coefficient here shown as k to the original image. So depending on the value of k, we can get different results. So if the value of k is 1, this is called unsharp masking. For values of k greater than 1, the process is usually called high boost filtering. So you see an example of this technique in the following figures. So here we see we have an original image of size 600 by 259 pixels, which is blurred in general. So to sharpen this, we use image blurring using a 31 by 31 Gaussian low pass filter with a sigma of 5, and this is the blurred version of the original image that we get. By subtracting this blurred version from the original image, we get the unsharp mask, and now if we sum this unsharp mask with the original image, we get this result, which is the result of unsharp masking. So for the unsharp masking, we used a value of k equals 1. We tested with a value greater than 1 here. In the last figure, the value of k is 4.5, and this is what is called a high boost filtering. As you can see, if I go back a little bit, since here we have both negative values and positive values, it is possible that after summing these two images, the unsharp mask and the original image, we go out of bound of the possible values that we can use for the image. So especially for the regions in which the values may be negative, we end up with these dark halos around the edges. So the value of k needs to be modified according to the result that we desire. Even though we haven't talked about Fourier transform yet, there are some great insight that we can get if we have a good knowledge of the fundamental properties that connect the spatial domain and the frequency domain. And these insights can help us understand how filtering works in general. So spatial and frequency domain linear filters are usually classified into 4 broad categories. We have low-pass filters, like we saw in smoothing filters, either box filter or Gaussian filter. We can have high-pass filters, like we saw in Laplacian or gradient filters, and we can have bandpass or Bandreject filters. The last 3 types can be constructed using low-pass filters. So Fourier transform is used to go from the spatial domain to the frequency domain. In effect, Fourier transform decomposes the signal, here image, into its consisting frequency components. So there are 2 fundamental properties that connect the spatial domain and the frequency domain. The first one is with regard to convolution. So convolution in the spatial domain is equivalent to multiplication in the frequency domain and vice versa. So that means that if we have the convolution of 2 signals in the spatial domain, in the frequency domain, that is equivalent to multiplying these 2 signals, more specifically multiplying their Fourier transform. On the other hand, if we have convolution of the 2 Fourier domain signals, it is equivalent to multiplication of them in the spatial domain. The other property is with regard to the impulse function. So if we have an impulse function of amplitude A in the spatial domain, it is going to be a constant function of value A in the frequency domain, and vice versa, which means that if we have an impulse function of amplitude A in the frequency domain, in the spatial domain, its transform is going to be a constant function of value A. So now that we saw those 2 fundamental properties, let's just see how we can build high-pass, bandreject, and bandpass filters from low-pass filters. So before getting to the equation, let's just quickly look at these figures on the bottom. So in a low-pass filter, what we have basically is 2 regions. One region is the pass band and the other region is the stop band. So a low-pass filter basically passes any frequency component that is inside its pass band and stops any frequency component that is inside the stop band. So now that we have this, you can see the connection between the low-pass filter and the high-pass filter. So in effect, a high-pass filter and a low-pass filter in the frequency domain, they are basically related through this equation. So a high-pass filter is 1 minus a low-pass filter in the frequency domain. But what is it going to be in the spatial domain? So in the spatial domain, we said that if we have a frequency transform that is constant, it is equivalent to having an impulse function in the spatial domain. And that is basically what we have here. So this one is converted to an impulse function in the spatial domain. So now let's just make it more complicated. What about the band reject filter? So a band reject filter has two passbands. So any frequency that is below U1 or higher than U2 will be passed through the filter, and any frequency that is between U1 and U2 will be stopped. So now you can easily see that the band reject filter is basically a summation of a low pass and a high pass filter. So the low pass filter has the frequency cutoff of U1 and the high pass has the frequency cutoff of U2. So in the frequency domain, the band reject filter is low pass 1 and high pass 2. So this signifies that the cutoff frequencies of these two are different. What about the band pass filter? So a band pass filter is 1 minus a band reject filter in the frequency domain. Again, band pass is 1 minus a band reject filter, and if we convert it into the spatial domain, we have delta minus the spatial kernel that is used for a band reject filter. Of course, more detail regarding these implementation will be discussed when we discuss Fourier transform in the next chapter. But let's just quickly look at one example. So here we see a sample test figure. As you can see, we basically have a circle, basically a filled circle with some hollow circles around it, and as you can see, the width or the frequency of these circles changes. So the frequency is kind of equivalent to the distance between the peaks of these circles. So as you go from the center to the end, as you can see, these distances become smaller. So in the frequency domain, that means that we have several components of different frequencies. So here what we have is the result of low pass filtering. So as you can see, any frequency that is higher than some cutoff frequency is smoothed, while the lower frequencies are kept intact. This is the result of subtraction of the original image with the low pass filtered one. Figure C, subfigure C shows the result of a high pass filter. Again, you see that these frequencies around the center, closer to the center, had lower frequencies, and they are smoothed out, while the higher frequencies are kept intact. This one is the result of having a band reject filter, and finally we have here the result of a band pass filter. Of course, as I said, we go into much more detail when we discuss Fourier transform in chapter 4. So we saw several techniques that are used for a spatial enhancement. So we saw techniques that only worked on single individual pixels to transform the intensity values to improve the contrast. Also, we saw some spatial enhancement techniques that either smooth or sharpen the image. So in general, digital image processing applications, we usually have to apply several of these techniques to achieve the desired result. So here we can see an example of such act. On top left corner, we have a nuclear whole body bone scan in which we want to enhance the skeletal details. The figure on top right is the result of the Laplacian operator. By adding the Laplacian to the original image, we basically get a sharpened image. Of course, since as we discussed before, using derivatives on images not only enhances the edges but also enhances the noise as well. The result is a bit noisy. To remedy this, we just combine the result of the Sobel operator. So here is the result of a gradient magnitude that is uh, obtained by applying the two horizontal and vertical kernels of the Sobel operator and then calculating the magnitude of the gradient by summing the absolute values of the gradient along the horizontal and vertical axis. Then we smooth this uh, Sobel image or Sobel uh, gradient magnitude image by a 5 by 5 averaging box filter. Then we mask the result of the Laplacian operator with the smoothed Sobel image. So to do that, we basically multiply this image with the result of the Laplacian, and then finally we add this smoothed or like this masked version of the Laplacian to the original image. As you can see here, we have a much sharper image but with less amount of noise. And finally, we apply a power law based intensity transformation to enhance the image contrast. Of course, as you can see, uh, several of these techniques that we discussed in this chapter are used. Of course, depending on different applications, you may use different technique or different combination of technique to get to the desired result that you want. So before jumping into much more details about Fourier transform and processing the images in the frequency domain, let's just have a quick introduction on why processing images in the frequency domain is very common. So before I start, let's talk a little bit about Fourier series and Fourier transform. So any periodic function can be represented as the sum of sines and or cosines of different frequencies, each one multiplied by a different coefficient. So let's just say we have this periodic function. By periodic function, what I mean is that this function is going to be repeated indefinitely. So as you can see, by looking at the function itself, it is very hard to see if there are sine and cosine functions that can create this. But if I use Fourier series transform, I notice that this function can be created by combination of these four sine and cosine functions that we have here. And this is the topic that will be covered in much more detail in chapter 4. But what about functions that are not periodic? So for those functions, we use Fourier transform instead of Fourier series. So any function that is not periodic but have a finite area under the curve can be represented as the integral of sines and or cosines of different frequencies multiplied by a weighting function. So to see why Fourier transform is useful, let's just quickly go back to the previous lecture in which we saw how having a separable or non-separable kernel can help us reduce the computational time. So for an image of size capital N, M multiplied by capital N, and a kernel of M by N, if the kernel is not separable, we needed to have M, N, M, N operations to find the convolution of the image. Convolution of the image with the kernel. We saw that if the kernel is separable, then the number of operations is significantly reduced to this equation. So now, if we do the same filtering in the frequency domain using fast Fourier transform, the number of operations is even lower. So it's going to be 2mn log 2 of mn. So here in these two graphs, you can see how much computational advantage we get if we use a fast Fourier transform instead of just doing the convolution in the spatial domain. So the first graph shows the computational advantage of FFT over non-separable spatial kernels. As you can see, for an image of size 2048 by 2048, if we increase the size of the kernel, what we see is that the amount of computational time is going to increase, but on the vertical axis what we show is the computational advantage. So it means that, let's say we have an image of this size and we want to process it or convolve it with a mask of size 201 by 201. So if we do this in the Fourier domain as opposed to doing it in the spatial domain, we get over 900 times computational advantage. So that means that we can do the same convolution in the frequency domain more than 900 times faster. For the separable kernels, the amount of computational advantage is a bit smaller, but in any case it is still beneficial to do large convolutions in the frequency domain as opposed to in the spatial domain. So for example, for this image, for an image of the same size and a kernel of 201 by 201, if the kernel is separable, if we do the calculation or the convolution in the frequency domain, we get a computational advantage of over 9 times. So that means that doing this procedure in the frequency domain is 9 times faster than if we do it in the spatial domain. Of course, for kernels of a smaller size, you don't get that much advantage. For example, if the kernel size is 11 by 11, doing it in the Fourier domain is actually more expensive because the computational advantage is less than 1. So in the next lecture, I will talk about the preliminary concepts that are used for defining Fourier transform and Fourier series. I will introduce Fourier series of periodic functions of one continuous dimension. I will also talk about Fourier transform of functions of one continuous dimension. Then I go over the convolution in the Fourier domain or in the frequency domain, and what is the relationship between the convolution in the frequency domain and the spatial domain. And also I will talk about sampling and Fourier transform of sampled functions.